It's not the pressure that you get when you take a test. You guys feel pressure when you guys take tests?
No.
Yeah.
The ACT test, pressure?
Not really.
Not really. Okay, don't care. A lot of people do, and they get a little test anxiety, and they get nervous, and I was the same way. I mean, I don't think there's anybody that... I felt good when I knew the material, and when I had read the question, I got this, I can answer this, you know, but it's when those ones like, I don't know how to... What? You know, and you try to work through it, and you just feel that pressure. It's not that pressure, okay? Or in sports, when you get up to bat, and what you're doing is you're just gripping tight because you're nervous and you don't want to fail, and you're supposed to be the opposite of that in sports. You need to be relaxed. The people that can find a way to relax and not, you know, let the pressure build up are usually the ones that are successful. They just don't let it bother them, okay? Or they minimize it. So, pressure basically measures a force distributed over an area. Thus, when you go fill your tire and you put the gauge on it, it measures it in what?
PSI.
What's the gauge measure?
PSI.
PSI. What's PSI stand for?
Pounds per square
Pounds force per square inch area. Okay? Pounds per square inch. But we don't use that a lot in science. If you talk to Maggie, who's a foreign exchange student, she has to get accustomed to English units like Fahrenheit. They say, well, it's going to be around 50 out today, and 50 in Celsius is, you know, like 120 degrees out, you know? So, and then even if, like we went over to Canada this year, and just everything on the Canadian weather is just, you know, it's Celsius temperature. The pressure's different. They don't say the atmospheric pressure is going to be 29.9 inches of mercury today. And they have it in kilopascals. So it's something that it's accustomed to her. Anytime we do with metric units, she's perfect with it, because English is like, you know, something that doesn't make sense. All right? So, does that make sense? Force applied over an area. So let me give you a little example of that. So, we're not going to plug numbers in or anything, but I think you'll get the idea. All right. Pressure is equal to force over area. We'll give you the units later. Okay? What if we do this? What's the size of P?
Quite large.
Okay? Is it bigger than this or smaller symbol?
Bigger.
Okay? So if that's a direct relationship, right? This gets bigger, pressure gets bigger. It's called a direct relationship. So you increase the force, you increase the pressure, keeping the area constant. Okay? So then the other one we would look at would be that.
So the P would be small. Oh, I do not understand.
So when the A gets smaller, the pressure goes up too. What kind of relationship is that? Indirect or inverse. Inversely proportional. Make sense? We've kind of dealt with that a little bit already. So, when you guys are explaining your explanation, you should have something related to force and pressure when something changes. And when we do our example, we'll kind of explain that a little bit. Okay? So we definitely know if you increase the force of the collision, forces colliding, something colliding is what we're talking about. Particles colliding something will increase the pressure. If the area is smaller, it's like a thumbtack. The one I usually use is a good example, and people really understand it well, is, Michelle, put your hand out. This is the thumbtack, that's the head side. I'm going to push it down in her hand. Hold your hand. Be strong. Okay? Good with that? Now I do it this way. And I say, put your hand out, and then I push down. What's going to happen?
What?
It's going to hurt, but it's going to go into her skin. If I push hard enough, we can get some muscle in there, and then maybe get to the bone, maybe too. Okay? Look at the area. I'm applying the same amount of pressure. Look at the area. Really, really tiny, big pressure. The thumb, that's the way a thumbtack works. You can apply a lot of pressure with your thumb, and then that's called like a mechanical advantage. You can apply a lot more. You're not applying more force, but what are you applying more? Pressure. You're applying the same amount of force. Okay? Applying the same amount of force. So, any questions with that? So gas molecules are moving in this room, and they're hitting our body, in our ear. Okay? And they are applying pressure to our eardrum. Well, you guys know what happens when you go and start on a day travel. You're down in Denver and you're going up to the mountains to ski. Okay? Your ears start to get uncomfortable, don't they? Because what's happening to the pressure outside the ear? It's going down. The pressure inside the ear is staying the same. So the pressure on the outside of the ear is getting less. Why is it getting less? What do you think?
Because of the altitude.
So you're going higher in altitude. What about the air above you? Is there more air above you or less air above you? Less air. When you're going up in altitude. Okay? There's less air above you. So if there's less air molecules moving, what kind of pressure does that create? Less. Right? Because there's less collisions. Does that make sense? You go up higher in altitude, less collisions, so less hitting your ear. The molecules on the inside, have they changed? No, when it builds up, and that's why you gotta like yawn or chew gum or... I never like to do that because I always think I'm going to blow my eardrums out. You know, I can do that.
You're supposed to chew gum, aren't you?
You can. You can yawn and try to open that up, so that then it equals out, right? So that's the deal with pressure and just some instances with it. When you go down, it does the same thing. I always think it's funny. We take a bag of chips to, a bag of something that's sealed. It's got a little bit of air in it, plus the food product. And then you start like here, and then you go up to the mountains, and then you get the groceries out to take into your condo or whatever, and the bag is fully inflated. It is puffy. Okay, it's almost ready to break its seal because there's so much. Well, has the air molecules in there changed? No. But there's less collisions on the outside and creates less pressure. Makes sense? So hopefully some of this you guys can internalize when you guys have to explain what's going on in these labs. Okay? Because number of molecules are important too. You get fewer or greater, that affects pressure and collisions. And then you just got to think about that when you do your explanation. Okay. So, let me give you some ways in which to... How is pressure... First of all, how is it calculated? So we've got that. Pressure equals force over area. And you guys will probably not have to use this equation. You won't have to use this equation to do any calculations. But I'm just going to show you where pressure comes from. The force that they use is not pounds in here. The force that we use is called a Newton. And a Newton is about 1/5 of a pound. So 1 Newton is about 1/5 of the pound in weight. Okay? That's kind of how they correlate. And then the area that they use in here is a big meter squared. So it's like this meter stick here, and we square it. Here by here. So it's probably similar to the size of this box. So the size of this box, we'll say, is about 1 meter squared, because it's a little bit, I would say that's about 1 meter squared. So think of putting 1 Newton weight is about 1/5 of the pound, and then spreading it all over this wall. Do you think that's a very big pressure? Think about it. About 1/5 of a pound. So we're talking about 4 ounces, weighted ounces, spread out over this whole area. Do you think that would apply much pressure? No, it's very, very small. It's a very, very small value in relation to like pounds per square inch, maybe, for example. Okay? Because an inch square is like, really small, and you got a pound on that. So you got 5 times that on that little square. So that is a bigger value. So what we do is we take pressure is equal to newtons over meter squared, and that is the same as 1 Pascal. They call it a Pascal. So these guys that do a lot of work in physics and chemistry, they're kind of given little, just how much they've contributed. There's a guy whose last name was Pascal, and they said he did a lot of work with gases and looking at properties, and came up with some really, Pascal's principle is one that we could look at. And so they said, we're going to go ahead and give you your own unit. I'm looking to try to get a unit after me one of these days. That'd be kind of cool. So. 1 gar. It's a 1 gar. Okay? And so then what they do is they abbreviate this into a PA. So that is like 1 PA. 1 Pascal. Okay? Make sense? So that's how you would measure it. You would measure the weight, you would measure the area, and you come up with this thing called a Pascal. Well, or that's how you calculate it. So how we actually measure it is with a barometer.
So many words I don't understand.
This is a barometer, okay? So a barometer is based upon air pressure pushing down on a liquid that's really, really heavy. This liquid is like 13 times the density or 13 times the heaviness of water. Okay? And it takes something really, really heavy to measure atmospheric pressure. If we put water in there, it would go through the roof and up about 30 feet. And then we could actually see a line we could measure.
Let's do it.
Okay? So water is not dense enough to where we can actually look at something and measure the pressure. Okay? So this is how a barometer works. So barometer just measure atmospheric pressure. There's different types. There's one that's called an Aneroid Barometer, which is just, you guys at home, do you have anything that kind of hangs on the wall and it's a needle and it kind of shows the pressure and how it changes? Have you ever guys seen anything like that? Okay, but they'll have them, and they're called Aneroid Barometers, and they're just a little box, and the little box will change its size due to pressures and differences in pressure, real sensitive, and then that needle will kind of move with that box, how it contracts and expands. Okay, so here's a barometer. A barometer measures atmospheric pressure. So how does a barometer work? You're wondering that, right?
Yes.
Okay, all right. So, real simple, crude way of looking at this. This is an open bath of mercury, Hg. Okay, it's liquid. Mercury's a liquid at room temperature. There's this tube, and we fill this tube. It's a long tube. It's about 1 meter in length. This tube is about 1 meter in length. We fill it with mercury. Then what we do is we turn it upside down in this bath. Have you guys ever taken water, filled something up, and turn it over in the bath? What happens to the liquid in the container? It what? Stays in there. Why does it stay in there?
Because there's no air to get in there and let it out.
That's one, there's no air to replace it, and air has pressure. So, there's no, I mean, that would be a start of that explanation. So, turn it upside down, and then what happens is that mercury level doesn't stay all in the tube. It actually, some of it goes down into the mercury. Now, if we're at sea level has standard pressure, about standard pressure. Their pressure changes a little bit, but they have this thing called standard pressure. And this mercury level, if it's at standard pressure, is going to be 760 millimeters high. So between this is 0 millimeters, 0 point, and up here, that distance between those 2 points is 760. That's on a meter stick. You would look on a meter stick and it goes, there's 760. Okay? Now, like I said, if it was water, it would go up 30 feet because density of mercury is 13 times more dense. So it takes a lot more force to move that up. So that's how they measure with a barometer the air pressure in here. So we could go over that room over here right now and say, oh, let's see, the pressure is 728. That's millimeters of mercury. So why isn't it 760? What do you think is not 760? Are we at sea level? Are we at higher than sea level?
Yeah.
Do we have less air above us or more air?
Less.
Less. You got that one right, didn't you? So, got less. Now, that goes up and down, right? Because we have these, on the Weather Channel, you guys watch, a high pressure is going to come in. What happens to the barometer? Does it go up or down? It goes up. Well, I got low pressure that's following that high pressure. It's going to bring us some nice weather, or it's cold weather. So then it goes down. So that's a gauge. It's a gauge that kind of help us kind of know what the weather is going to be like. Okay? So that's how they measure it. So this is a measurement, and this here. In a second, I'm going to give you all the standards because we want a standard to work with. We don't want to work with this. So just like a meter stick's a standard, 1 meter, we're going to have a standard for pressure. We're going to make everything that pressure. Now this can also be symbolized as torr. So like if you go to the hospital on that and they have things that's measured in pressure, they might have something in torr. They might say 760 torr instead of millimeters of mercury. Okay? And it's just named after a guy named Torricelli, he's an Italian physicist. Okay? Named after him. So 760 torr. Okay, so we know that pressure is force over area, and this is how we can calculate it. We can take the force divided by the area, and we can calculate and get a Pascal. Okay? We know how we can measure it with the barometer. It measures the pressure pushing down. So see, the air pressure is pushing down on this mercury bath, forcing the mercury up. And that's what causes that mercury to stay where it's at. Okay? So we got 2 units. Well, actually 3. But 2 of them are the same. Millimeters of mercury and torr are the same. So we got pascals, we got millimeters of mercury, and so then we're going to bring them all together. We're going to simplify this, and we're going to make it just a value that's easy for us to use when we talk about pressure. And it's called atmospheres. Okay? So that's what we're going to do. So I need you guys to write this out because this is what you're going to use to do some conversions. Not today, but later on. So 1 ATM is that unit we're going to use to simplify when we deal with pressures. So we got this thing called 1 ATM. That's going to equal 760 millimeters of mercury, which can also be represented as torr. So those are synonymous. 760 torr, same as 760 millimeters of mercury. Okay, this ATM stands for atmospheres. It's called 1 ATM is 1 atmosphere. And then 760 millimeters of mercury. So now we're going to tie in that Pascal. Remember we said that Pascal is 1 Newton per meter squared. That's a calculation, and we have to tie it into the barometer measurement. So we do that, and it's 101.3, but it has to be, since it's just a small unit, Pascal, we have to put a kilo in front of it because it's so small, and for it to equal the pressure in the standard pressure, you need what's called kilopascal. So this is kilopascal. Okay.
No, I'm pretty sure the sun rose this morning.
So questions you have on that. So these are the units we'll use to convert. Yes?
So the 101.3 kilopascals, is that the same as 101,000 pascals?
Yep. Yep. So this is the same, you guys don't have to write this down. This is the same as 101,300 pascals. And remember, a pascal is a Newton over a meter squared. So it's 101,300 newtons over a meter squared. That's what atmospheric pressure is. But all we have to do is use kilopascals. Okay? So this is important for you guys to do calculations later on to go back and forth. So I'll do one real quick for you. It's really easy. Okay? I'm not going to have you do many examples because you guys know how to do it. After you see one example, you'll know how to do it. So I have something that's 500 millimeters of mercury. How many atmospheres is that? Go ahead. I'll see how many can calculate it right. So I want to know the atmospheres of pressure. Okay, I got 500 millimeters of mercury. Tell me how what the pressure is in atmospheres. I'm not going to have you raise your hand if you got it right, but I bet you 90% of you will get it right. Because in chemistry, as well in physics, if you guys take physics next year, everything is unit driven. And if you know the conversion, and you know how to set up your new units to convert, it's something with, as science teachers since your freshman year, been really, really pushing you to know how to cancel out units. Okay? So the answer would be 0.66. Okay? And real quick, if you didn't get it right, you just take millimeters of mercury. You say, well, for every 760 millimeters of mercury, I have 1 ATM. Boom, I got my answer. Yes?
Do we have to do that, or can we just do that?
It's up to you. If there's a problem, yeah, it's up to you. Okay? Any questions with that? All right. So now I'm going to get to a question that you had to do for tomorrow and go through it. Okay. There's one thing I wanted to get to in temperature today, but we'll do it tomorrow. Tomorrow, if you miss, we're going to get you accustomed to the lab quest and how it works, and have you do some little mini experiments to kind of see how to set up your experiments, how to do all those things tomorrow. It'll just kind of be a play day with the lab quests and how they work. Okay?